Okay, so in this video, we're going to look at the angle bisector theorem. And so the angle bisector theorem is similar to the perpendicular bisector theorem, where perpendicular bisector theorem says the perpendicular bisector point is equidistant from the ends of the segment. An angle bisector, well, there isn't endpoints for it to consider when you're talking an angle bisector. Instead, you've got the sides of the angle. So the angle bisector theorem says if a point is on the angle bisector, if a point is on an angle bisector, then it is equidistant from the sides of the angle. And so as long as it is on the point is on the angle bisector, then it's equidistant from the sides. Now, note what that means is it's a point equidistant from sides. And so what we are looking at is how do I calculate the distance from a point to a line? And so we need to remember the way that we do that is by drawing a segment in that is at a right angle to the line through the point, and the length of that segment is the length from the point to the line. That's how you always calculate it. So what this theorem is saying is if you've got an angle, and on that angle, you draw in an angle bisector, then if you have a point on that, the distance from that point to one side and then to the other side is going to be the same. So let's go ahead and prove this theorem. When we prove this theorem, we're going to start off, we'll use this picture over here as our guide. We'll call those points B and C and then D. And so we'll say that AD bisects angle BAC. And that's what's given to you. You're given that you have an angle bisector, right? It says if a point is on an angle bisector, and so it's a given. And then we know that BD is going to be perpendicular to AB, and DC is going to be perpendicular to AC. And the reason for that is by construction, because that's where we constructed those as perpendicular, because that's how you determine the distance from a point to a line. And so we needed them to be at right angles, and so you can always construct a perpendicular line through a point. And so wherever that point is, whether it's a midpoint for a perpendicular bisector or a point off the line, you can always construct a perpendicular. So now we want to prove that BD is congruent to DC. That's what the theorem says. It's equidistant from the sides. So to do that, we're going to show that this triangle is congruent to that triangle. Well, from the given, we're going to know that angle BAD is congruent to angle CAD by definition of angle bisector. And then we're going to know that angle DBA and angle DCA are right angles. That's from this. And so all I've done up to this point is done the two logical conclusions from those first two steps. And that's by definition of perpendicular. Now I need to look at this to see, am I going to use hypotenuse leg, which means I can leave them as right angles, or am I going to use something else? And it turns out the way I'm going to prove it is if I've got this angle congruent to that angle, then I can show these two angles congruent, which gives me two angles. And then I just need the side, which is going to be AD by reflexive. And that's going to allow me using angle side to prove the triangle's congruent. So to carry that out, we'll say angle DBA is congruent to angle DCA by right angles are congruent. We know that if we have two right angles, then we can set them congruent to each other. And then we have AD is congruent to itself by the reflexive property. And that's enough by angle side, because we've got angle side to prove that triangle BAD is congruent to triangle CAD by angle, angle, side. And then that is enough to prove our theorem, which is BD is congruent to DC. And that is by CPCTC. So that's our proof for the angle bisector theorem. So it does have the name of angle bisector theorem that you can put up here as well when we use it. Okay, and then there is a converse to that theorem. And so theorem 5.5 says that the converse of the angle bisector theorem, so the angle bisector theorem says that if a point is on the angle bisector, then it is equidistant from the sides. And so the converse of that is, if a point is equidistant from the sides of a triangle, then it is on the angle bisector. So if a point is equidistant from the sides of a triangle, then it is on the angle bisector. Okay, and so again, we won't go through and do all this proof, but let's at least prove it in our brains. We just won't formalize it. So this time you want to show that if I draw in from here to here, and I know that this is congruent to that, we'll call these. And so we know that AD is congruent to DC because we've got this point that is equidistant from the sides. So we need to show that BD is an angle bisector. Well, to do that, we would show that these are right angles because that's how you measure the distance from a point to a line. This is a leg, which we know is congruent. BD being congruent to itself is a hypotenuse. So by hypotenuse leg, I know that these two triangles are congruent, which would then be enough to show that those two angles are congruent to each other by CPCTC, which is then enough to show that BD bisects angle ABC.